So with this question, a car, right, 800 kilograms, so its weight is 800 g, is traveling on a horizontal road. I've got that here, and it says it experiences a resistance to motion, and that's important. It's constant throughout the journey. Okay, so it stays the same, this resistance. You'll notice in my force diagram here, I've put R to represent resistance. Okay, because of course R is what resistance starts with. So it's okay to do that, right? Because we don't know what it is. We're going to work it out later. But if I'm going to call my resistance R, that means then my reaction, I can't call that R as well, can't I? I've got to use a different letter. So use the letter N in this case, because of course N stands for normal reaction, yeah? If you think about normal reaction, that's what the full name of it is. So we put N there. Of course, the other thing I need to put here is show the direction of acceleration. But it says here the car accelerates from rest, okay, so in other words, U equals 0 at the start, under constant tractive force of 300 newtons. So that's why I put 300 newtons there. Now, tractive force, right, is just the result of the force that's been created from the engine, okay? So the power that comes from the engine is creating the forward moving force, okay, it's pushing it forward. So that's what it means by tractive, right? That's the pushing going forwards there, and it's constant again, notice, yeah, it doesn't change, it stays at 300. After 50 seconds, the car reaches a speed of 15. So when t is equal to 50, we get v equals to 15. So part A then says calculate the magnitude of the acceleration of the car. Well, I can actually use the equations of motion, okay? So I can use the equations of motion because we've got constant forces, okay? So it's important to recognise the wording in this question. They always said the forces were constant. If the forces were constant, that means then the acceleration is also constant. Okay, so we could use the equations of motion when the acceleration is constant. So to get A here, of course, if I got u, t, and v, I can use v equals u plus at and sub it in. So final velocity is 15. Initial velocity is 0, acceleration is what we want to work out, and time is 50. Okay, so to get the acceleration there, all I've got to do is take that 50 over and divide. Okay, so I've got 15 divided by 50, of course, will be 0.3 then. Okay, that will be meters per second squared. That's part A. Part B then says calculate the magnitude of the constant resistance to motion. So this resistance here, right, this what's pulling it back. It could be anything, right? It could be air resistance, right? It could include the friction as well, everything, right, combined. So we want to calculate this resistance here. So what we'll do, we will use Newton's second law in the direction of motion. Okay, now we need to have the resultant force, remember, equals to mass times acceleration. Now the resultant force isn't just going to be this 300 newtons, don't forget, right? We got the 300 taking it forward, but we take away what's pulling it back, okay? So we have the overall effect, right? Because it's not 300 newtons that's having the overall effect of this car, because there are forces which are pulling it back. So it has less, if you like, then. It's not as much as 300 overall, okay? Because of these resistant forces. So that's my resultant force. That will equal to mass, which is 800, times the acceleration. Of course, by acceleration, I worked out in part A to be 0.3. Okay, so then you've just got to do a bit of rearranging here. Okay, and you can get your R. Okay, so we have 300, take away 800 times 0.3, and we get 60 newtons, of course, for R. So that's the resistant forces, is 60 newtons. Okay. We go on to part C, and it says when the car reaches a speed of 15, the engine is switched off and the car is brought to rest by constant braking force. Notice again that word constant braking force. Total distance covered by the car for the whole journey is 500 meters. Find the constant force exerted by the brakes. Okay, so they've given us the whole journey here, distance is 500 meters. Perhaps what I'd be interested in is how much of that journey are they braking for, okay? And, you know, if we take note of the first line, it says when the car reaches a speed of 15, the engine is switched off, and of course the car then is applying that braking force. So we could perhaps work out the distances travelled up until that point, up until the point it gets to 15. Okay, so remember then, U was 0, isn't it? T was 50, okay, for it to get to 15. So we can work out then what is. How far has it travelled until it gets to 15, meters per second. So using then the equations of motion again, because remember it was all constant forces acting, we could use that one. So S will equal, well, U is 0, so that'll be 0 times 50 plus half times A, which remember was 0.3. Okay, so I've worked that out as well. I could have put that there. Times then T, which is 50 squared. Just put that in. And I get out 375 meters. So it travels 375 meters, then the engine is switched off. So if it travels in total, what's the whole journey total? 500 meters. So basically then, 500 take away 375 meters is 125 meters. Okay, so in a way it's slowing down, it's decelerating for 125 meters. Okay, the remaining time of the journey. Now, because of course it's a constant braking force, we can work out what the acceleration is. So now if we think about it, it's going from 15 to 0 to rest, work up the acceleration, and it's traveling 125 meters. Okay, so we can work out what the acceleration is for as it's slowing down. So using v squared equals u squared plus 2as. V of course is 0, u is 15 plus 2 times a times 125. So on my calculator then, I can work out a from there. So it'll be minus 15 squared, divide by 2 times 125, which equals to a. So that implies that a will equal 0.9 or minus 0.9 meters per second squared. Okay, that's the deceleration. So we've got the deceleration. Now, of course, then we want to work out what this constant braking force is. Another diagram will help. Okay, appreciate now there's no forward force. There's no 300 newtons pushing it forward. We've just got the braking force, which we could call maybe B. Okay, braking force. But remember also, we've also got that resistant force. That resistant force is got to be there as well, because it's there throughout the whole journey, it said at the beginning. Okay, remember that? It says constant throughout the whole journey, throughout the journey. So that was 60 newtons, wasn't it? Now there's nothing going forward because the engine's been switched off. So when we apply Newton's second law, okay, nothing going forward, you just got these resistances, you've got take away 60, take away B. That's what the resultant force is going to be. Equals then to mass, which is 800, times then the acceleration, which is minus 0.9. And it's the case then of plugging that into your calculator to get B. So minus 60, if you take that over, let's just work that out first. So we've got 720 there, and then you can get your B by doing minus 60 plus 720, so B will equal 660 newtons.